Electrochemistry Part 1, Electrolysis and Electrolytic Cells. Electrochemistry is that chemistry which deals with changes that are caused by electrical current, or it deals with the production of electricity by reactions. All electrochemistry occurs through redox reactions, where we have oxidation and reduction processes. Electrical current is charge transfer. Electrical current can be transferred either through metals, through pure electrolytes, or through electrolytic solutions. Electrolytic solutions will be a dissolution of an electrolyte in solution. For a pure electrolyte, the electrolyte has to be in a fluid phase, or fluid state, which means that the atoms have to be free to move. Generally, since most of our electrolytes will be ionic substances, that means that the ionic substance has to be in a liquid form or molten. Transmission of electric current usually occurs by an electrode. Now, in metallic conduction, where we're transferring charge through metals, the electrons will move independently of the atoms. That means they can jump from atom to atom without the actual atoms moving. And there's no real change visible in the metal. This is something that will occur with, say, a copper wire, where a copper wire can transmit electricity from one point to another through the copper metals. An electrolytic or an ionic conduction occurs as the charge moves with the particles. This will occur in a state where we have either a pure electrolyte or an electrolytic solution. And so as the individual charged particles move through solution, that current moves with them. In an electrochemical process, the reacting system is referred to as a cell. An electrolytic cell is a cell in which the electrical source is external. It comes from some other outside source like a battery. And an electrolytic process is going to be a non-spontaneous process. So the input of electricity from an outside source forces the non-spontaneous process to occur. A voltaic cell has an internal electrical source. And this comes from a spontaneous process where spontaneous production of electrons occurs. And a voltaic cell will actually produce electricity, while an electrolytic cell consumes electricity. So a voltaic cell can be used to power an electrolytic cell. Now, electrodes, as mentioned earlier, are the conduit for electrical charge, and in a cell, the electrodes will be the surface for which the oxidation or reduction processes can occur. So if we have a electrode in an oxidation process, that's the process, or the electrode is the surface on which the oxidation occurs. And for a reduction process, it occurs on the electrode for the reduction process. Now, electrodes can be either reactive or inert. If electrodes are reactive, they will actually participate in the reaction. If they're inert, they simply serve as a surface on which the reaction occurs. Now, the two different types of electrodes are cathodes and anodes. Cathodes are electrodes on which reduction occurs. And for a cathode, the species that is reacting at the cathode will gain electrons. The anode is the electrode on which the oxidation process occurs, and here the species will lose electrons. The term cathode and anode is backward from cation and anion. We can also think of the cathode as being the electrode to which the cations would go to be reduced. The anode is the electrode to which the anions go to lose their electrons. Now, the cell itself overall will combine what we call half cells, which are equivalent to half reactions in an oxidation-reduction process. The oxidation half reaction, where the loss of electrons occurs, is the anode. The reduction half reaction, where the gain of electrons occurs, is the cathode. Now, the sign of each electrode, whether it is a positive electrode or a negative electrode, depends on the cell type. An electrolytic cell will have a negative cathode and a positive anode. A galvanic cell or voltaic cell will have a negative anode and a positive cathode. Electricity will always flow from the anode to the cathode regardless of the type of cell. It's just a question of whether or not it's flowing from a negative to positive or from positive to negative. If we look at this example here, we have electricity flowing from the positive end into the battery and then out the negative end. So we're flowing from positive to negative, and since we always move from anode to cathode, moving from positive to negative means that we have to be moving from a positive anode to a negative cathode and be an electrolytic cell. And that would make sense given that we're connected to a battery in the diagram, and the connection to a battery is going to provide an external source of electricity. Now, if you look at the colors of the little dots moving, the blue dots are moving to the negative side, the red dots are moving to the positive side. The red dots would represent our substances which need to move to the positive end, which is the anode. The anode is where we're going to do an oxidation, so the red dots will be the anions moving to the oxidation process. The blue dots will be the cations moving to the reduction process. Now, looking at electrolytic cells, these are non-spontaneous reactions that require electrical energy. And the process that occurs in an electrolytic cell is called electrolysis. We generally will insert electrodes into a solution and connect them to some sort of direct current source. As an example, the down cell is an electrolysis of sodium chloride. Now, if we look at this diagram, the way that this functions, we actually will take molten sodium chloride. So we have the ionic substance, electrolytic substance in its liquid form rather than being as a solution. The molten sodium chloride is heated and has a current pass through it. We have if we imagine this being cut in half basically, there's a ring on the inside of the down cell which is made of iron and serves as the cathode. There is the graphite anode in the middle of that ring. And as the sodium chloride moves into this internal chamber, the sodium will be reduced from sodium plus to sodium metal at the cathode, and the graphite will serve as an anode upon which the negative chloride ions are oxidized to form chlorine gas. The chlorine gas escapes through the top of the down cell and out through into a collecting chamber. The sodium metal will actually float on top of the molten sodium chloride, so it moves into this side ring, so to speak, that then will pull it through into an external source where it can be collected. So we can collect the sodium off to one side and the chlorine off to the other side. Now, in the down cell, we conduct this electrolysis from molten sodium chloride. And passing the current causes sodium and chlorine to be produced at the different electrodes. The sodium reduced at the cathode, the chlorine oxidized at the anode, have to be kept separately. Now, the electrons will enter through the cathode and be lost by the anode. So the cathode will be negative, the anode will be positive. If we look at the process, chloride goes to chlorine with the loss of 2 electrons. Sodium will gain 1 electron to make sodium metal. Now we have to have 2 of these to balance the reaction overall to get 2 electrons on both sides, giving us a net reaction of sodium plus chloride minus yields sodium metal plus chlorine gas. Now this is non-spontaneous below 801 degrees Celsius. The direct current will actually force the electrons from the positive to the negative in this case. We keep the products separate because any sort of contact between the sodium and the chlorine will cause a highly reactive, explosively reactive production of sodium chloride back again. So what we just produced as chlorine and sodium would revert back to sodium chloride explosively. As we saw, the structure of the down cell is produced in such a way as to make sure that this doesn't happen. Now, the down cell is the most practical production of sodium metal. We produce chlorine as a byproduct, but it's not the primary source of chlorine for use in different processes. The electrolysis of aqueous sodium chloride is actually how most chlorine is produced in an industrial process. Chloride is produced at the anode as an oxidation process, and hydrogen is produced at the cathode in this case. And that's a reduction process. We form hydrogen and hydroxide from water. Sodium doesn't actually get reduced in this electrolysis because water reduces more easily than sodium does. It forms less reactive products. Reactive metals like sodium tend to not be reduced from solution. If I were to put those reactive metals in water, they would actually generally form metal hydroxides like sodium hydroxide. So the overall process is chloride forming chlorine, water forming hydroxide and hydrogen. And so the net production is water plus chloride going to hydroxide plus hydrogen plus chlorine with sodium ions as spectators. If I evaporate the solution, I'll wind up with sodium hydroxide, and this is the primary means by which we produce sodium hydroxide and chlorine gas. Now looking at the electrolysis of aqueous sodium sulfate, we see that both hydrogen and oxygen gases are produced. So we have hydrogen produced at the cathode and oxygen produced at the anode. The solution near the cathode will be basic, and the solution near the anode will be acidic. In this case, water is both reduced and oxidized in this process. If we have water gaining 2 electrons will produce hydrogen gas in hydroxide. Water will also go to oxygen plus hydrogen and 4 electrons. So we're overall going to be producing both hydroxide and hydrogen in this process, liberating hydrogen gas and oxygen gas. Our net reaction is taking 6 waters, producing 2 hydrogens, 1 oxygen, 4 H pluses, and 4 OH minuses. Now looking at this, we can combine the H plus and the OH minus back into water. So the net reaction producing 4 water on the right-hand side, using 6 water on the left-hand side, is that 2 waters form 2 hydrogen gas plus an oxygen gas. This is what happens when we run current through a solution of sodium sulfate. Water is both more reducible and more oxidizable than either sodium or sulfate, respectively, and so it serves as the species which actually undergo the oxidation reduction. In this case, the sodium and the sulfate simply serve as electrolytic ions and are able to conduct electricity through the solution and to close the circuit overall. An electrolytic cell is usually made to make some sort of commercial element. We can make sodium or chlorine from sodium chloride. We can make other compounds, metals from other compounds, things like aluminum or calcium or any of these other group 1A and 2A elements can be produced, with the exception of barium, to form different metals. Electrolytic cells are also sometimes used for metal plating because they can deposit metal of one type on the surface of the electrode. If we use something like jewelry, in which the jewelry itself serves as the electrode, we can deposit thin plating of gold or silver on that jewelry and make gold or silver plated jewelry by doing an electrolysis process on the substance, using the jewelry as the electrode for the process.